Hello, everyone. Give people another couple of minutes to show up. Hello, Hussein. Oh, where's that truncated? So I've posted a link in the chat a couple of times. That link is to some videos that have been recorded by Frank. Those are to go with his tutorial from this Tuesday. So you can go check those out for proofs for a couple of those greedy problems from problem set 3. Yeah, so before we get started, the one thing I need to mention is that the slides have been updated again. So this time the changes are to sections 3.2 and 3.3. I did clean up one or two things in the earlier sections, but it's not important for, it's like, how to put it, nothing of significance has changed. But yes, the section 3.2 especially, the one we're about to do first today, that's had some fairly extensive changes, and section 3.3 has also been changed. So please fetch the updated slides from Moodle. So we'll get started in a minute or so. Today's lecture is on more graph algorithms. Why are they out of focus? Okay. The first section will be on single source shortest paths, so finding shortest paths from one vertex of a graph to everyone else. You should be familiar with this already. It's just Dijkstra's algorithm. But we'll go through the proof of correctness as well as the implementation using different data structures, which you may or may not have seen to some extent. And our second topic for today will be minimum spanning trees, where we'll mention Prim's algorithm briefly, but we'll focus on Kruskal's algorithm and again the data structure required to implement that efficiently. Okay. So yeah, today will be Dijkstra's algorithm and Kruskal's algorithm. After today's lecture, you will have all the information required to complete assignment 2. And remember that assignment is due on Thursday. Okay. I guess it's time to get started. So As I mentioned, our problem is in a directed graph with non-negative edge weights and a source vertex S, where there is a path from S to every other vertex. We would like to find the weight of the shortest path from S to every other vertex. I'm remembering I forgot to mention something. That's fine. Yeah. All right. So this is a single source problem. We are interested in only the shortest paths from S to everyone. Shortest paths from everyone to everyone is a different problem that we'll do later on in the course. And note that the edge weights are non-negative. This will be important in our proof later on. And again, the case where negative edges are allowed will come up later in the course in the dynamic programming topic. Okay. A couple of disclaimers here. First, the framework that we used was a directed graph, but you can just as easily apply this to undirected graphs. In an undirected graph, you can simply treat each edge between vertices u and v as a pair of edges, one going from u to v, and the other one going back from v to u. And then you have a directed graph with the same properties. So you can now run the algorithm that we're about to develop. And also note that I've spoken about the shortest path from S to V. This shortest path isn't necessarily unique, but that doesn't matter too much for us. We just know that there is a minimum weight that can be achieved by a path from S to V, and if there's more than one way to achieve that edge weight, that's fine. Sorry, path weight. Okay, so hopefully you are all familiar with Dijkstra's algorithm, which is the greedy algorithm which solves this problem. We'll go through an outline of that algorithm and resolve some of the questions that are still left to be answered. So the algorithm goes as follows. We have a subset of the vertices for which we have found the shortest path weight. Initially, this is no vertices, and then we'll progressively add one vertex to this at a time. In terms of how we represent this set, simply a Boolean array. So initially, every entry of the array is false, and as we add vertices to the set, we change one entry of that array to true at a time. We also need to maintain for every vertex a value dv, and that will be the weight of the shortest known path from S to V. What do I mean by the shortest known path? Well, this is the shortest path where all the intermediate vertices, that is all but the last vertex in the path, are in S. So initially, the shortest known path to the source itself should of course be 0, but because we don't have anything in the set S, the shortest path to everything else is infinity. We don't know of any paths from S to other vertices yet. Yep. As we add vertices to the set S, we will then update the relevant dv values. So at each stage, we are going to pick a vertex to add to S, and the way we're going to do that is we'll pick the vertex outside S, which has smallest dv value. That is, the smallest value of the smallest path weight from the source to the vertex V in question, using only intermediate vertices chosen from the set of things that we've already seen. This dv value will be the length of the shortest path from S to V, and then once we've added V to S, then this may change other d values, because now there is one more vertex that you can go through as an intermediate on your way to other vertices Z, so you may need to update some other dz values. Right? Again, you should all be familiar with this. This Dijkstra's algorithm is covered in the prerequisite course 2521 or 9024. But this algorithm still leaves some some questions to be answered, right? First, this is a greedy algorithm, right? At every stage, we would like to go from set S containing nothing to set S containing all the vertices. That is, having all the vertices answered. But there are some choices as to how to do this, and our choice was to always add vertices one at a time, just greedily picking whichever is of smallest d value outside of the set S, and so the choice to do this must be justified. Yeah. So our first matter will be to prove the correctness of this greedy idea. Second, we said that when we add a vertex v to the set S, we had to update some of the tentative distances to other vertices. So I've just said do all the updates, but it remains to be seen for which vertices we have to do these updates and what updates are necessary. We've also talked about a bunch of values dv, where one value is associated to each vertex. This is vague and deliberately so, because I haven't specified what data structure I'm using. Again, we'll look at a couple of different choices here and their impact on the time complexity of the algorithm. Okay. So first, let's have a look at the correctness. That is, the correctness of the greedy idea, where we add one vertex at a time by choosing that which, outside of S, has the smallest dv value. And so the claim that we're interested in is, suppose we have some partial set S containing some of the vertices, and we're about to add a new vertex v. We would like to confirm that that the distance to this vertex that we've found, the tentative shortest path or shortest known path, which uses only intermediate vertices that are within the set S, we'd like to prove that this path length is the actual shortest path from S to V, right? So let's consider the proof. So we know that we define dv to be the length of the shortest path from S to V, where the only intermediate vertices allowed were those within the set S itself. So we were not allowed to consider paths that go outside of S on their way to V. All right, so let's call such a path P, and we'd like to consider in what cases might this not be the shortest path overall. So if there were to be some better path from S to V, i.e. if the claim were to be false, then there must be some other path P dash which leaves S at some vertex Y and then continues on to reach vertex V, right? Let me just flick forward for a bit. So in a sense, path P would be the top route, yeah, from S to V, kind of directly, where all the intermediate vertices are within the set S, and then you take one edge to leave S and go to the new vertex V. The kind of path that we're considering as P dash is the bottom route, where you don't take all intermediate vertices within V, you instead follow up, within S. Instead, you travel within S for some portion, and then you leave S to a different vertex Y, and then follow one or more edges from Y to get to V. Right? So P is the top route from S to V. P dash is the bottom route, which goes via Y. And we'd like to argue that the path length of P, which we defined as d sub V, that this is the correct shortest path from S to V, and therefore it's better than any other path of the form P dash. So we'd like to prove that the top route from S to V is necessarily no worse than the bottom route. How do we do this? Well, you may observe that the path P dash, which goes from S to Y and then on to V, must first consists of a path from S to Y and then some stuff. And that's the key observation. So the portion of P dash which goes up to Y, well, that is a path from S to Y where every previous vertex was within the set S. And by definition, this was one of the candidates for the shortest known path to Y. And therefore, this part of the P dash path must have weight at least D sub Y. Yep. D sub Y is the shortest known path from S to Y with only intermediate vertices within the set S. And this is one such path. So P dash, just considering the part of P dash up to the vertex Y, has length at least dy, and as we continue on from y to v, we take some more edges. Each of those edges contributes non-negative edge weight, and so the whole path P dash, the bottom route from S to Y and then on to V, also has weight at least dy. Yeah, it's not necessarily strictly greater than dy. All of those subsequent edges might have weight 0, but certainly it's at least dy. So we have a top route with path weight d sub v, and a bottom route with path length at least d sub y. How do we compare these? Well, v and y are both outside the set S, right? And v was the next one to be added, which means v must be the one outside S which has smallest d value. So v was chosen because it had the smallest d value among all the vertices outside S, and that includes y as well, which means that d sub v is less than or equal to d sub y. The left-hand side term is the weight of path P, and the right-hand side term is a lower bound for the weight of path P dash. And therefore, d sub v is correct. It's the shortest path from S to V because it can't be beaten by any other path from S to V that goes outside S elsewhere. All right. So again, what we're saying here is that the top route, where you stay within S and then go to V in the best possible way, cannot be beaten by any other path that was not considered for d sub v, because as soon as you go outside to some other vertex y, you've already incurred at least d sub v cost, and then you need to continue on to v, taking potentially some more edges. All right, I'm going to stop here for a sec and give you guys an opportunity to ask any questions that you might have before we go on. So here the old S is before we add V, the new S is after we add V. And you can see that Y is outside of that frontier because it was not the next thing to be added. Okay, chat's very quiet. So can I ask you to at least tell me, are you convinced by this? Are you convinced that the next thing to be added should always be the thing that is closest to S, and that this is going to be correct, that this is going to correctly calculate the shortest pathway from S to each vertex in turn? Yeah. And therefore, if we repeat this at every stage, correctly answering one vertex will answer the shortest paths for everyone. Okay, good. Yeah, like as a note in general, if you are convinced of something, also tell me, right? Like, it's of course good if you are not convinced and you have questions. That's great. Please let me know. But likewise, if you are convinced of something, it also helps me if you nod along, so to speak, because I can't see you nodding. All right. Cheers. Okay, people happy with that? It's good. So now that we're convinced of the correctness, the next question to answer is, what do we mean by update other dz values? And what updates exactly are required by this? When I add a vertex to S, I now potentially open up some other paths to other vertices Z, right? You know, the dz value is always the shortest known path. That is the shortest path that goes entirely within S and then takes an edge out to the new vertex Z. Now, this might be still the same. It might still use the same vertices as before, but now that we have one extra vertex in my set S, I should consider paths that go through V on the way to Z. And so for some of those vertices outside S, outside the new S, we may need to change the dz values. And it appears like you might need to consider updates to all of those other vertices. But in fact, we can do a bit better than that. Suppose there's an outgoing edge from our new vertex V to Z. Then we need to consider updating the shortest path to Z. Because of course there are two candidates now for the shortest path to Z. There's the shortest known path from before, which took things from the old S and then went to Z. But we also have a new way of getting to Z by taking the shortest path to V and then one more edge from V to Z. Yep. So we check whether this is an improvement, whether dV plus the weight from V to Z. We check whether this is an improvement on what we know already, and if so, we update the dz value accordingly. Now, you may point out here that this isn't the only way that I could get a new path from S to Z, because you might go from S to V and then onwards to something else within the set S, and only then go to Z. But in fact, this is never an improvement on the existing dz value. In fact, these outgoing edges from V are the only time that you have to consider an update to dz. Let's see why that is. So the claim here is that if dz changes by when we add V to S, the new path, the path that is better than the old dz, must have its penultimate vertex at V. In other words, the last edge of this path must be from V to Z. Why is this the case? Well, let's consider the alternative. Suppose there is suppose the best path from from S to Z is now not of this form, but rather going from S to Z with some other penultimate vertex U. So it's a new shortest path, but its second last vertex isn't U, it's something else. How is this possible? Well, for it to be a new shortest path, it must go through V and then continue on to other vertices within set S before finally going to Z. But maybe you now see a bit of a problem here. Hang on, let's just have a look at the diagram again. So the old shortest path to Z might look like the bottom route, where we go from S, follow some vertices, go to some other vertices within S, and then head out to Z. But we now have to also consider paths of the form of the top route, where we go to V along the shortest path, along a path, maybe shortest, and then continue on to some other vertex within the old set S, and finally take our last edge from U to Z. Can the top route ever be better than the bottom route? Again, I hope it's clear that the answer is no. The part of the bottom route which goes up to U can't be beaten by going through V first. And that's what we're about to prove. So we said that the new path P, which we're about to consider, goes from S to V, then to U, and finally takes an edge to Z. But we know that there's an even better shortest path from S to U without going through V. There's a path P dash, which simply is the shortest path from S to U, and it doesn't have to go through P, it doesn't have to go through our new vertex v because u was added to s before v was. At that point, the shortest path was already known, didn't need to go through v. Of course, we are not taking just this shortest path from s to u, we are also adding on the edge from u to z. But even so, taking the shortest path to vertex u plus this extra edge, this path is no worse than the p that we just found, but it's a candidate for the shortest path to z. And indeed, it was a candidate for the shortest path to z before v was added, and so the weight of p dash, the top root, is no better than the one of the candidates, which is the bottom root. So the weight of p dash is greater than or equal to the previous dz value before we even added v, and therefore we have a contradiction. There can't be a new shortest path which goes through v on the way to something else in S and then onto Z that is better than the existing dz value. All right. Certainly the path from S to Z, if its penultimate vertex isn't v, then this cannot be if the penultimate vertex isn't v, then it can't be a new path and also better than the dz that we knew about already. Yeah. So the bottom root was already a candidate for d sub z before we added v. The top root is one of the new candidates for d sub z, but it can't be any better than the bottom root that we had before. Which means that the only kinds of paths that we need to consider are paths where the last vertex is the second last vertex is v. Those are the only paths which might beat the ones that we had before. And so the only updates we need to do are along those outgoing edges from v to external vertices. And again, the update is a very simple procedure. It's just compare dz to dv plus that last edge and make the update if necessary. If we had access to each of these, if we had some kind of random access to these vertices, to these dv and dz values, then we could do this in constant time. Depending on our data structure, we may need more time than this to access values, but we'll see how we go. All right. Again, I'll take any questions here. In fact, I think now's a good time for a mini break, so to speak. So we'll give you about 4 or 5 minutes to ponder this, and we'll start again at 33 or so. But yeah, happy to take any questions on these two proofs before we go on. I'll just return to the outline slide. So far we've confirmed that this is a correct algorithm, and that the last phrase, the update other dz values as necessary, just means along those outgoing edges from the new vertex v, consider updating the destination, the shortest known path to the destination of that edge. We don't need to worry about any other vertices outside S. Those can't be beaten by paths to v and then back to some other u. Casper asks, how do you define a set S? Oh, gone all blurry. Yeah, it's initially empty. So S is just a subset of vertices which are solved. It's initially no vertices, and then we add one vertex at a time. The first vertex to be added is the source vertex itself, because we'll first solve the shortest path to the source vertex and get that distance is 0, but then we'll add one vertex at a time, always adding whichever is of shortest distance among the unsolved vertices. Okay, we're dropping less frames today, which is good. I'm not quite sure why why we had problems yesterday. Yeah, hard to tell really. Perhaps someone with more technical knowledge than me could work it out, but yeah. Okay. So, what's left to do? Well, we mentioned earlier that there are four main issues that we've yet to really resolve. Correctness, done. Updates, done. The next is the choice of data structure for the DV values. So let's have a look at a couple of choices here and see what impacts they have. Okay, so we'd like to pick a data structure to maintain the DV values. Let's consider what operations we do with those DV values. One operation is find the vertex outside S with smallest DV value, that is the one that has to be added next. And the other operation is, sorry, that's a typo. That should be VZ, not WZ. My apologies. For each of its outgoing edges, update DZ if required. Yeah. So for each outgoing edge from the new vertex V, we need to make some updates. So we need to find the minimum minimum DV values, considering only vertices outside S, and we need to make some updates. Let's consider how to do this with an array. And then we'll consider some more sophisticated choices. Well, one more sophisticated choice, I suppose. So, first some notation. We'll suppose the vertices are, suppose there are n vertices labeled 1 through n, and m many edges, and vertex S will be the source, so S is one of these labels from 1 through n. Okay, so all we're going to do in this first attempt is to store the DI values in an array. So these will go in so D1 will be the shortest known path to vertex 1, D of S will be the shortest known path to vertex S, and so on. And then at each stage, we need to pick out the V to be added and make updates. So we'll pick out the V by just scanning through the entire array. So we'll do a linear search of array D, ignoring those vertices which are already in S, and then we will select the vertex V outside S with smallest dV value. That vertex will be the one that we're going to add to S. Then, for every outgoing edge from V to some other vertex Z that's outside S, we consider updating dz. Of course, the update is as before. We just compare dz to the value of dv plus that last edge weight and update dz to whichever is smaller of those. Okay, so I think this is the simplest implementation that we could consider for the algorithm that was presented earlier. It's not wrong, but we'll see that it has some limitations. So what is the time complexity of this algorithm? Let's consider what we do. We said at each stage, and each stage corresponds to adding one of the vertices. So that linear search of array D runs n times. Now, there isn't a convenient way to skip, like, how to put this? This runs through actually all n vertices n times, because we still need to look over all the elements of S before we move on to non-elements. But you know, this is only changing it between n squared and n squared over 2, so it doesn't really matter. But yeah, so certainly for each of n vertices, we're going to do a linear search. So that is, the first step takes order n time, and it runs n times. The second step is the one that we have to be a bit more subtle about. Here we're considering all the outgoing edges from my new vertex to other things. And it might appear at first that there isn't a convenient way of talking about this, but in fact there is, because every edge is considered only once in this entire procedure, right? For each new vertex, we consider all its outgoing edges, and every edge is outgoing from something, which means that for every edge, we eventually consider it in that second dot point exactly once in the entire running of this algorithm, which means that this second step runs m times in total, and the update procedure for dz is constant time. So the update procedure runs in constant time, at most once for each edge, and therefore we can say this algorithm runs in n squared plus m time. N squared time is spent on the first step, spent on the first dot point. M time is spent on the second dot point. Any questions about that? Yeah. Every edge is outgoing from some vertex V, and when you get to that vertex V, you process that edge. So every edge gets processed once. Of course, some of those edges will be from vertices V to other vertices U which are already solved, and so you don't need to do anything for those edges. But yeah, we get down to M. Now, how big are n squared and m? Well, if we're working with a simple graph, that is, we don't have self loops and we don't have parallel edges, then the number of edges can't exceed the number of vertices squared. At worst, you may have an edge from every vertex to every other vertex, so that's about m equals 2n squared. Sorry. No, m equals n squared. Indeed, we can simplify that slightly to n times n minus 1, or n squared minus n. So a time complexity which adds n squared and m, n squared is the dominant term in that. So we can simplify this down to just n squared. Now, a little bit of a disclaimer here. If the graph is dense, that is, it has close to the maximum number of edges, this is okay, right? If if we consider, for example, a complete graph where every possible edge appears, then you can't do better than this, because certainly you can't solve the single source shortest path problem without going over all the edges. Yeah. So in dense graphs, this is not too bad, but often we're dealing with graphs in which this is not the case. That is, most of the possible edges are not actual edges in the graph. So we should consider what happens when m is much less than n squared. Can we do better in these cases? So here we should return to the drawing board a bit. Maybe the data structure that we used is not the best one in general. So let's think of the two operations that we wanted. We wanted to find the vertex outside of S whose dv value was smallest, and we also need to update along each of the outgoing edges. Again, copy paste bug, sorry. And of course, the part of this that has been slow so far is the linear search. This is probably a pattern that you've noticed a few times, including the tutorial exercises. If you're doing a linear search for a minimum or maximum, this is often the part that is slow, and hence the part that we might seek to improve with the data structure. So, so far, we're looking for the smallest dv value by doing a linear search, and this has to be run n times because you need to add vertices one by one. So this is where the n squared in the time complexity comes from. If we can improve on this, then we may be able to lower the time complexity. So let's consider alternative strategies. I mentioned earlier that this isn't exactly just a find minimum, right? We're not just looking for the smallest dv value overall, because we have to skip over those vertices already in S. If it was just a find minimum without consideration of which vertices we're allowed to pick, then we'd always be picking the source vertex because its shortest path is 0. Yeah? So 0 is certainly going to be the minimum of these. But we can get around this. We can transform the first operation into a exactly find minimum by just deleting things that we don't need to look at anymore. So as soon as we add vertex v to S, we don't want to consider this dv for the minimum anymore. It's no longer a candidate. So what we'll do is delete this value dv from the data structure containing the d values. Once we do this, we will now actually be looking for the minimum of the remaining dv's in the next step. So we've now changed our 2 operations into 3. But these 3 operations are find the minimum of the remaining d values, delete this minimum d value, and finally update any of the d values. Yeah, update any as opposed to say update minimum. Now, what data structure appeals to you in this setting, where you have to find minimum, delete minimum, and run some updates? At least the first 2 should give you some hints. Okay, Hussein, deleting dv, no, it doesn't mean changing the original graph at all. It means that whatever data structure we're using to store all the dv values, originally it was an array, and what I'm saying is actually physically delete that entry from the array. So we no longer keep track of the like when we're going for the minimum next time, we don't consider this entry. Yeah, so it's deleting it from the new data structure, the collection of all the d values. Yeah, so many of you have got the right idea. We want to use a priority queue. A min heap priority queue is great for finding the minimum of the remaining entries, and also for deleting the minimum of the remaining entries. However, the heap that we've presented, for example, in lecture 2, doesn't let us do updates. It doesn't update arbitrary elements. Sure, you can update the minimum element by removing it and inserting something different, but when we go to update the DZ values, we're not always updating the minimum entry. We might be updating anything at any position down the heap. So we'll need to make some modifications to the heap that we've presented earlier in order to support arbitrary updates as well as the usual heap operations. Okay, so that's the next thing we're going to present, which is the augmented heap data structure. So first, let's talk about the implementation of the basic array heap. The simplest way, I think, to implement a heap is to use an array which simulates it. So the array will the heap array will be indices 1 through n, and the way that the tree structure is implicitly represented within this array is that the left child of aj is stored in A of 2j, and then the right child in the next entry. So it looks something like this. Yeah. So, if you tilt your head and look at this, you will see a full binary tree emerging. And indeed, we'll maintain the heap property accordingly. So we'll make sure that the smallest thing is in A1, that A1 is smaller than A2 and A3, A2 is smaller than its children A4 and A5, A3 is smaller than its children A6 and A7, then 4's children will be 8 and 9, 5's children will be 9 and 10, 10 and 11, 6's will be 12 and 13, 14 and 15, and so on. Alright, and in this way, we can store things in an array while implicitly maintaining the structure of a full binary tree and hence a heap. Okay, so this is, so far we've only talked about the standard heap, and we're yet to talk about the modification we do to that to enable arbitrary updates. But yeah, I think this trick may be new to some of you, so so let me know if you have any questions about that. But yeah, in this way we can quite efficiently use the n entries of an array to store the n entries of a heap and keep them in this kind of order. Of course, the heap operations where you bubble up or bubble down various entries can just be done by swapping any element with its parent and so on. How do we determine whether we put a value in entry 2 or 3? It doesn't matter. In a heap, we just need, in a min heap, we need the root to be smaller than its 2 children. The order between A2 and A3 doesn't matter. So you can switch around the left subtree with the right subtree, and it's still a valid min heap in the same way. Yeah. So right now I'm just talking about the heap in general. We'll then introduce the augmented heap, which does a bit of extra bookkeeping to support updates, and then we'll once we've established that the augmented heap does everything we want to do for Dijkstra's algorithm, we'll return to the Dijkstra's algorithm with that modification. Okay. Now, what are these elements? Well, when we talk about storing the DI values, storing the DV values in the heap, we may just think literally that, put the D values at the various entries of the heap. But I'm going to modify it slightly. I'm going to store not just the D values, but a pair of vertex and its d value. So each entry of the heap will look like some vertex, comma, its dv value, and I'm going to maintain the min heap property with respect only to the dv values. Okay, so associated with every value in the heap is also the vertex which gave rise to that value. And this is going to be important for looking things up later. So I mentioned that we need to do some extra bookkeeping. So, okay, let me try that again. Up to now, this is just a basic heap. It does everything that, it does all the find minimum, delete minimum, insert, all of that in log n time, just like the heap that you've seen before with an explicit tree. Yeah, this is just an implicit way of storing that same heap. Yeah, so hopefully you're convinced that up to now you can run all the usual heap operations in log n time, and this is all fine. But of course, this standard heap doesn't let you do updates to things other than the minimum element. Of course, you can kind of hack your way around updating the minimum element by removing it and inserting something else. Updating somewhere down the heap is not something that you can do directly because you don't have access to update the element corresponding to a specific vertex. For this, we're going to do some extra bookkeeping. That bookkeeping is in the form of the position array P, and that's going to store at which index is each vertex represented. So, whenever the jth entry of the heap refers to vertex I, that is, it stores the pair vertex I shortest known path to I, we're also going to correspondingly record that the position of vertex I is j in the heap. And this means that we can look up the information relating to vertex I using the property that a of p of I is a of j, which is the information about vertex I. So if I always look up a of p of I get back vertex I, comma, the distance to vertex I. All right. So let me now. Actually, I'll show you an example, and then we'll flip back to the actual heap operations. So here's an example of a heap with 7 entries. Each of the heap entries is a pair consisting of vertex, comma, the distance to that vertex. So the minimum entry is the distance of 1 to get to vertex 7. You can then go down the heap. Oh, sorry. Let me just turn, okay, fine. Cool. As you go down the heap, you'll see that every vertex has smaller d value, that is smaller second entry, than the second entry of its 2 children. Yeah. So if we just look at the second entries, 1 is less than 2 and 6, 2 is less than 3 and 8, 6 is less than 7 and 9. So we have indeed maintained the heap property here. Again, this physical tree is not being represented directly, but rather we store it implicitly with this heap array. And then I'm also going to maintain this position array, which lets me do lookups into the heap. So how do we represent this? Well, we simply list off in the heap array each layer of the tree from left to right. So a of 1 is the root of the tree that has vertex 7 with distance 1. And so that's the reason for the first column in the AJ table. The second entry in the heap is the left child of vertex 1, that is of the left child of the root. And so that is vertex 6 of the graph with distance 2, and so on. So for example, the fifth entry of the heap, we count down and we say that it's the left child of the root and then the right child of that. 1, 2, 3, 4, 5. That's the pair 4, 8. So that's vertex 4 and distance 8, and that again occurs at position 5 marked in cyan. Likewise, position 7 of the heap, we walk further along the, further to the right in this level, and we find the pair 3, 9. And finally, what does the position array do? Well, the position array lets me do kind of reverse lookups. It lets me say, if I'm interested in vertex I, which index of the heap array should I be interested in? So for vertex 1, well, that occurs in the second last position of the heap array. So that's index, of the entire heap array, the index with first entry 1 is index 6. So that's why P of 1 is 6, and so on. And now we can put it all together. We can do A of P of I to get back information about vertex I. Take, for example, A of P of 3. First, P of 3 is 7, and then A of 7 gets me back the pair 3, 9. So, A of P of I tells me about vertex I. All right. Any questions? So the top table is just a regular heap. The second table is some bookkeeping, which keeps track of where everything is. Because, if I just gave you the original heap, if I just gave you the heap array, you can't quickly look up which entry of that array corresponds to vertex 2. The extra bookkeeping that we do in the position array lets me directly access that, okay, vertex 2 is considered at entry 4 of the heap array. That's the whole point of that second array. All right. So now we can look at the heap operations. Of course, the regular heap operations, that is insertion, deletion, and access top, these run in the same time complexity as before. You do have to do the extra bookkeeping because, for example, when you pop the heap, there's some swaps involved. And each of those swaps has to not only swap entries of the heap array A, but also swap entries of the position array P. But this just adds a constant factor, so we don't mind. The improvement comes from now being able to change the D value associated to vertex I. This was not an operation we could do before because we didn't know where vertex I was in the heap. But now that we have this position array, we can indeed look up P of I, which is the index J at which the pair is stored, and now we can update by changing the second entry of A of P of I. Of course, the new value might not respect the min heap property. And so you may need to bubble up or down to restore that heap property. In this case, we're only ever reducing D values, so only bubbling up applies. Let me show you what I mean by that. Suppose I took that suppose I changed A of P of 3, so I changed the distance to vertex 3 from 9 to, say, 5. So we have this, we'd first say, looking up the position array, vertex 3 is stored at index 7 of the heap. Now I'd go into the heap array, A, and look at index 7, where I have the pair 3, 9, and I'd make my update by reducing that 9 to 5. But now I have a small problem. This no longer respects the heap property because the new value 5 is smaller than the D value of its parent, right? Its parent was the pair 5, 6, and so the new D value of 5 is smaller than 6. And so what do? I simply swap these two entries. So I'd swap the 3, 9 pair with the 5, 6 pair. This corresponds to one swap in the A array. So I'd swap that pair. And I'd also have to swap the positions of vertices 3 and 5. But once I've done that swap, I'll then compare the pair 3, 9, which just moved, to its new parent, and see that no further swaps are required. and we're done. All right, so we do this bubble up procedure, and because there are only log n levels in this tree, because it's a full binary tree, the bubbling can take at most log n time, and therefore we can now support arbitrary updates, that is, update the distance to particular vertices in log n time, and that's exactly what we wanted. All right. So now that we're able to support the three operations that we care about, which are access top, pop from the top, and do arbitrary updates, we can now use augmented heaps to implement Dijkstra's algorithm. So we'll store the DI values in an augmented heap of size n. And then at each stage, we first find the vertex v that we want to add to the set S, the solved set, by, again, just taking from the top of the heap. This finds the vertex v with smallest key, and as we're going to see, we pop that element d sub dv, or rather the pair v comma d sub v from the heap. And this means that it's not going to be considered in future, so that indeed, as we go on, the minimum in that heap is indeed the minimum, only considering vertices outside of set S. And finally, the last step is, for every outgoing edge from V to some Z, update dz using the usual update procedure. So that is, change dz to whichever is smaller of the existing dz and the new dv plus that edge weight. And again, we process this update in log n time using the augmented heap. This last step is why the position array was necessary. Okay. So again, we should analyze the time complexity of our algorithm. There are n stages as before. Okay, constructing the heap takes n log n time, of course. In fact, it takes n time. There's ways to construct a heap in n time, but it's not going to matter because later steps are going to take n log n anyway. So I'm sorry I've forgotten to include that, but building the heap itself takes linear time. Then we can proceed as follows. In each of the n stages, we need to access the top of the heap, which takes constant time. We need to delete from the heap, which takes log time. And then finally, just as before, for every edge, we need to run our update procedure. But now our update procedure might changes something in the heap. And because there might be some bubbling involved, it's no longer constant time. It's now a log time procedure, which means that for each of n vertices, we do log n work to pop it from the heap. And for each of m edges, we may need to update the shortest known path to the destination of that edge. How are you implementing pop? So the pointer to the top of the heap is always just the first index. Remember, a of 1 stored the root of the heap. So the way that we do pop is we delete that entry, we replace it with the we replace it with the last thing, and then we bubble down. Okay. So yeah, you can revise that. That's like the pop operation is no different to the usual heap that you've seen in Comp 2521, just with the extra bookkeeping as before. Okay. So in total, the time complexity is n plus m times log n, but we know that m is no less than n. Yeah. For example, since there's a path from from S to everyone, sorry, that's a typo. Since there's a path from S to everyone, then every edge, every vertex other than S must have an incoming edge, and so the number of edges is at least the number of vertices minus 1, and so we can simplify this to simply m log n. Now, I do need to make a disclaimer here. You may have seen it mentioned in Comp 2521 that Dijkstra's algorithm can be improved to m plus n log n time. That's true, but it requires the Fibonacci heap, which is a data structure beyond what we've taught in this course or any other course. And for that reason, we will not let you use this time complexity for Dijkstra's algorithm, precisely because you don't know the data structure that's involved. If you really want, you can look this up and provide all the details of that data structure. So you may wish to look through textbooks and so on for those details, but you must reproduce those details. You must prove the time complexity of the various operations and so on. Yeah, this is definitely not required for anything that we do in this course. So I can't forbid you from using things that are true, but I'll say, it's not recommended, and if you wanted to use it, you'd have to do a bunch more work than is actually required to solve the problem. Okay? William, that's not exactly it. We don't leave empty space at the end of the array because we still need to maintain that A1 is the root, yeah? So what we do is, to pop something from the heap, what we do is we swap the top thing with the bottom thing. So we delete the 7-1 by replacing it with the very last thing, 3-9, and then we just record that the size of our heap has gone down by 1, so that 7-1 has been eliminated without changing the shape of the tree. That is, maintaining that it's still a full binary tree. However, the new entry 3-9 might be too big. In fact, it definitely is too big. So we now need to bubble that down to restore the heap property. All right. The way we bubble that down is we swap it with whichever is smaller of its children. In this case, it would bubble down on the left and then on the left again. Yeah. So once you pop this, that 3-9 will get replaced to the top, and then it will move to the left and left again. The new root will be 6-2. Its left child will be 2-3, and the left grandchild will be 3-9. Everything else in the heap will be unaffected. Okay, and that concludes our study of Dijkstra's algorithm and single source shortest paths in graphs with non-negative edge weights. Yeah, let's take a break here, and then we'll proceed to the minimum spanning tree problem. We'll take, say, 7 minutes. We'll start at 1:15. Okay. Again, let me know if you have any questions, and if not, great. Take a break. Okay. Kay asks about writing proofs. I think my biggest advice here is use the tutorial exercises. So problem set 3 uses greedy algorithms to solve various problems, and our solutions are written up to assignment standard. So you can have a look through the proofs presented in those solutions, and I particularly suggest going along to those tutorials where we explain those problems. Some of those have been done already. In fact, most of the ones other than graph algorithms have been done, but by all means, you can show up and make requests, and we'll do our best to honor those. And there's a couple of tutorials later next week where there's nothing scheduled as per se, but tutors will prep 1 or 2 hard problems as well as taking requests from you guys. Yeah, I think the written solutions are also a really great resource for writing those proofs. Yeah, the templates are really common styles of proof. Yeah, so you're looking for that should help you structure your proof, and then the details of why exactly the greedy stays ahead at each stage. That's going to depend on the particular problem that you're doing. I'm sorry, it's a bit vague because it's kind of difficult to answer that question because it is such a general one. I think in terms of like an exchange argument, you want to identify what the stages are at which your greedy algorithm makes choices, and then consider what if there's another sequence of choices that was made. Can I argue as to why that sequence is no better than the one I did by substituting one of their choices for one of my choices every time we diverge? That's the broad strokes of an exchange argument. As for a greedy stays ahead, you're looking for some heuristic which like some metric of partial that adjudicates partial solutions. And again, you're saying that at every stage, I'm better than everyone else, or I'm no worse than everyone else using this metric. And as we extend that to the final stage where we've completed our selection or whatever, at that point, I will have beaten every other algorithm. Finally, those are useful particularly for problems where you're selecting. There's also types of problems where you do optimal ordering, and that's where you may want to consider, why is my order better than all others? Well, if there's a particular order that has an adjacent inversion, what happens if I swap it around and resolve that adjacent inversion? If that's guaranteed to improve things, well, then I can just keep making a sequence of those swaps, and it's kind of an exchange argument in that way as well. All right. Let me just check one more thing and then we'll carry on. Okay, good. I'm glad to hear it. Okay, let's continue. All right, so our last application of greedy algorithms will be for the minimum spanning tree problem. Again, something that you should be familiar with from your earlier studies. So first, the definition: a minimum spanning tree of a connected graph G is a subgraph of G with the same vertex set, and our subgraph must be a tree. So this constitutes a spanning tree, right? A tree which spans all the vertices of G. For it to be minimum, it should have the smallest possible total edge weight among all other spanning trees. First, we're going to propose a fact about minimum spanning trees, and then we'll use this to develop our algorithm. So our lemma here will be that if I have a connected graph where all edge weights are distinct, then say we have some subset of vertices S. So it's a non-empty proper subset, meaning simply that it has some but not all of the vertices. Then consider all the edges between that subset and the outside of that subset. So all edges across that frontier, right? Then the smallest length edge among all of those must belong to every single minimum spanning tree, of the graph. Okay. So I know there's a lot on that in that block. All this is saying is, suppose I have some set of vertices S, and outside this is S complement. Okay, so I've got this kind of setup. I designate some particular subset of the vertices, and the rest of the vertices will be in S complement. Then, of all the edges crossing this frontier, that is between S and not S, in the case where all edge weights in the graph are distinct, then the cheapest of these edges, say E, this edge must belong to every single minimum spanning tree of the graph. Intuitively, why do we expect this to be true? Why is this edge E going to be in every single minimum spanning tree? Well, the reason is, why would you ever take E dash? Why would you ever take E dash? If you instead took E dash, which has greater weight, well, then there's going to be some path between these two. And there's going to be some path between these two. Yeah, exactly. There has to be some connection between S and S dash. And if you took E dash instead of E, well, this minimum spanning tree can now be improved by deleting E dash and taking E instead. Yeah. So let's have a go. Let's write up a formal proof of this. So again, assuming all edge weights are distinct, and I have some subset S containing some of the vertices, then what happens if I take a minimum spanning tree which does not contain this edge E? So instead of taking the cheapest edge between U and V, we instead take a different edge between P and Q. So because C is a spanning tree, there must be some way to get from U to V, right? In a tree, there's always a unique simple path between two vertices. And so if we're not taking the direct edge from U to V, we must instead be going from U to V via some other sequence of edges. And let's say that the first of these edges, the first edge on this path to cross this frontier between S and S complement, is from P to Q. So this path from U to V must leave S using some edge PQ. But as we mentioned, the edge between U and V is shorter than any other edge that goes between S and not S. So replacing that edge PQ with the edge UV is going to produce a new tree because every pair is still connected, has the same number of edges, but we'll have reduced the total edge weight. So in fact, the tree T that we constructed was not minimum. And so this is a contradiction. We can show now that no minimum spanning tree can omit this cheapest edge crossing the frontier. Good. So based on this observation, there are two famous algorithms which solve the minimum spanning tree problem. Both algorithms have some commonalities. They start with a whole bunch of n isolated vertices, and then we add edges one by one, building up a forest. But when I say a forest, I mean that we have several trees that are not all connected to each other. But there's a difference in how they actually add those edges one at a time. You may be familiar with Prim's algorithm. Prim's algorithm says, well, I start with n isolated vertices, and then I designate one of them to be my single connected component, and I add one of the other vertices to it at each stage. So at each stage of Prim's algorithm, I have one large connected component and a whole bunch of isolated vertices. How does Prim's algorithm work? It's basically the exact same as Dijkstra's algorithm, but instead of considering the whole path length from S to the new vertex Z, I just consider the last edge from V to Z. That's the only difference between Dijkstra's algorithm and Prim's algorithm. The implementation is otherwise identical. So all you do is add the vertex closest to S rather than the vertex that is closest to... Sorry, what am I saying? There's a typo here, that's why. So you're not adding the vertex with smallest entire path length. You're adding the vertex with the smallest last edge crossing the frontier. That's the only difference. We're not going to spend a bunch of time on Prim's algorithm here. We're going to instead work on Kruskal's algorithm because it's more interesting to see a different technique, I think. I'll also mention that the earlier disclaimer about the Fibonacci heap version of Dijkstra also applies to Prim's algorithm. So just like Dijkstra's algorithm, there is a Fibonacci heap version that runs in m plus n log n. The same is true of Prim's algorithm, and again, you can't use it in this course unless you go through all the extra work of actually detailing how it works. Not something that we're interested in doing. Okay. All right. So, how does Kruskal's algorithm work? First, we sort the edges in increasing order by weight. Then, for every edge, we ask, should I include you? What I mean by that is, we go through the edges in order and we ask, for every edge, if I added you to the forest that I've built up so far, that is the bunch of trees, would that introduce a cycle? If it would introduce a cycle, I throw out the edge. If it does not introduce a cycle, then I take that edge. And we finish when all the edges have been considered, or equivalently, we finish when n-1 edges have been added, because now the forest is connected, everyone's joined to everyone, and we won't want any of the future. We won't want any of the future edges to be added. Okay, so once the forest becomes a single tree, then we're done. So the claim is that Kruskal's algorithm does indeed produce a minimum spanning tree, and furthermore, if all the edge weights are distinct, then this minimum spanning tree is unique. We're just going to prove the second claim. The first one kind of follows from it, but we're not going to spend time on the proof here. So let's consider that we have a partial forest where we've added some edges, so we have a whole bunch of small trees, potentially some isolated vertices as well. And suppose we're about to consider edge E, which is between U and V. And this edge is something that actually gets added according to the execution of Kruskal's algorithm. And we're going to ask, is this edge actually compulsory? Is this giving us the unique minimum spanning tree, or is there a better way to build a minimum spanning tree without choosing this edge? Again, this is an exchange argument. In essence, we're saying, what if there's a different minimum spanning tree which didn't pick E and made some different selection of edges? We're going to show that whatever other edge was picked, we can pick E instead, and it's in fact strictly better. So This edge E that we're about to add in Kruskal's algorithm joins vertices U and V. Now, let's consider the one end of that, say U, and we're going to identify S as the set of vertices that are reachable from U within this forest. That is everything in U's little tree. Certainly U is in S because U is in the tree itself, but V should not be in S because we're only adding the edge between U and V because there isn't an existing path between U and V, right? If U and V were both in S, then this edge UV would not get added by Kruskal's algorithm. It would get discarded instead because adding it would create a cycle. Now, we need to justify why this edge between U and V is a compulsory edge to take in any minimum spanning tree. And indeed, if all the choices we make are compulsory, then certainly the minimum spanning tree is unique. Well, why is this the case? You may observe, of course, that this kind of fits the framework of the previous lemma, because we have edges between U and V, and we're saying of all the edges crossing that boundary, we want to take E in every single minimum spanning tree. Well, to prove this, we need to confirm that E is indeed the smallest weight edge that crosses this partition. In other words, we need to confirm that the original graph doesn't have any edges shorter than E that cross the boundary between S and not S. Of course, if such an edge existed, then it would have been considered earlier in my sorted order because I did it by increasing order of weight. And at that point, when we considered that edge, it would have the same property of joining two vertices that aren't previously connected. So that means that that edge would have been chosen, and that would cause V and U to both be in set S. In other words, V would be reachable from U, and that contradicts what we've established before. So, again, to recap, when we're up to edge E, just before we add it, U and V are not connected, which means that any shorter edge joining things reachable from U to things to V itself, any shorter edge joining things reachable from U to things not reachable from U, no such edges can exist, and therefore E is the shortest of those edges, which means edge E is compulsory to take in every single minimum spanning tree, and so according to that lemma, it must be chosen. And so the set of edges that Kruskal's algorithm takes, every single one of those belongs to every minimum spanning tree, but of course a minimum spanning tree only has n-1 edges, so indeed Kruskal's algorithm gives us the unique minimum spanning tree. There were no other choices to make, right? If there are n-1 edges that you chose, and every single one of them you didn't have a choice, you had to pick that edge, then this is the only way to build a minimum spanning tree. So we are done. All right, again, I'll leave the continuation of this to cover trees with repeated edge weights for you to look into if you'd like. But in this course, we're happy for you to take that as granted, right? So you can safely assume that the rest of the proof regarding duplicate edge weights works out fine, and Kruskal's algorithm is correct. What we're going to be more interested in is how do you actually implement this? We've said sort the edges by increasing order of weight. That's easy. That's a thing that we can do. Sorting is a solved problem. But we've also said consider for each edge whether you can add it or not. You add it only if it doesn't create a cycle, and that's not so straightforward, right? Visually it's quite easy to do, but how does it actually work in practice? How would we write an algorithm to do this? That's a little more complicated. And for this, we're going to need a new data structure. So, as we said, we need to be able to quickly determine, given a new edge, would it introduce a cycle or not? And as we've mentioned up to this point, the test is, are the two vertices already connected? i.e. are they in the same connected component already? So for example, if our forest looks like this, with 3 small trees, some edges are okay to add, others are not. For example, if I considered any of these three edges, I should not add any of them, right? The 3 edges marked in red are all bad edges to add because they create a cycle. And the reason for that is they join 2 vertices that are already connected by a sequence of other edges. They're already in the same connected component. However, edges that go between 2 different connected components, like these ones, these are fine. Yeah, if you add either of these 2 edges, you join 2 different connected components, and therefore you don't make a cycle. Any questions about that? So we need a way to quickly determine, given 2 vertices, are they in the same connected component or not? Of course, these connected components partition the vertex set into a whole bunch of disjoint sets. And that's where the union find data structure comes in. So the union find data structure partitions a big set, such as our vertex set, into several disjoint sets, and it supports 3 operations. First is just construction, where we initially put everything into its own singleton set. This is straightforward. The interesting operations are find A, which is find some label of this set to which element A belongs. We want this operation to run in constant time. So we want in constant time to be able to look up which set does A belong to, and we need this answer to be somehow representative or canonical, so that if I ask this of 2 different elements, the answer is equal, that is find A equals find B if A and B are in the same set, and they're unequal if A and B are not in the same set. Finally, I need to be able to merge 2 sets together. If I just flip back for a sec, when I place that either of those green edges, I'm now joining together 2 connected components into a single larger connected component. So I need to be able to union 2 sets together. And so the union operation takes 2 sets whose labels are A and B and merges them into a single set, A union B. And here we need to be a little bit careful. The way we'll implement union find, we can't give we can't give a useful bound for a single union operation, but we'll guarantee that the first k union operations run in total k log k time. So a little bit more on that. Again, the one union operation might take up to linear time, but instead a sequence of k union operations, the first k, we will guarantee that runs in k log k time. This is so-called amortized analysis. So this says, rather than a single operation having a guaranteed time, a sequence of guaranteed, I can achieve a better bound by looking at a sequence of these operations and the total time taken by them, and therefore I have, again, loosely speaking, an average cost for every operation in that sequence. So here, any one union operation might be linear time, but in total, the first k of these union operations takes k log k time, and therefore, on average, each one takes log k time. Of course, you're not going to make more than n-1 operations, so n-1 unions, because you'll only have one set left at the end of that. So this reduces the time taken by unions from, any one of them might take linear time to, on average, they take log n time, loosely speaking. I just want to clarify one point though. I get some questions about this sometimes. Is this the same as average case analysis of time complexity? It is not. These are 2 fundamentally different things. When we talked about average case or expected runtime, this was a probabilistic statement. Yeah? That's not what's going on here. In this case, we're talking about an aggregate. So it's the average of 10 things. It's the average over 10 operations. And I know for certain that the total of those 10 operations doesn't exceed some amount, as compared to in most cases, the operation takes this much time. And depending on the input, it might take worse. Yeah. So they're two fundamentally different ways of analyzing things. Amortized analysis is not the same as expected case or average case analysis. These are two different things. Okay. So let's talk about how this union find data structure actually works. What we're going to do is, for every set, I talked about it having a label. The label is just going to be one of the elements of the set. I'll call this the representative of the set. Okay, so every set has a captain, so to speak. So the way we will talk about implementing union find is as follows. We have three arrays. The first array A is the label array. Is the label array. This means that every element, every entry of that array records AI equals J, where this means J is the label of I. In other words, element I belongs to whichever the set with representative J. The second array is B, the count array. This is saying for every element I, how many things call me their representative. So, array A records the captain of every element of the entire set. Array B records how many things call me captain. Finally, array L is the list array, and this contains pointers to the head and tail of some linked list containing all the bi many things whose representative is I. Now, after the first union operation, there are going to be some things which are not the representative of their own set, which means they're not the representative of anyone. In that case, bi is 0 and the linked list is empty. And while the list array isn't actually required for our application in Kruskal's algorithm, it is sometimes useful elsewhere. So we include it. It doesn't make things more difficult to analyze, so we'll include it for now, but we don't end up using it. So it's the least priority thing to follow. Hussein asked, does the representative have to be a certain element, or is it fine if it's any? It's a good question. It's fine if it's any. We will kind of, for the definition so far, we're just going to say that the representative of the set is just some arbitrary element but we're going to next talk about the implementation of those operations, and we're going to see that this does place some constraints on how we pick the representative. So how do we initialize? How do we make union find? Well, we put everything in a singleton set. So everything belongs to a set on its own, which means everyone is their own representative. Because you're the only thing in the set, you have to be the captain, right? So initially, every AI is just I itself, every BI is 1, and every list array, every entry of the list array just contains pointers to a singleton linked list. But then as we do unions and finds, we need to do some interesting stuff. So, initializing is easy, right? You make everything its own captain. AI is I, BI is 1. How do we do find? How do I find the representative for a given entry I? Well, that's easy. You just look it up in the A table, right? A, the label array, stores everyone's representatives. So if I want to know element I's representative, I just look up AI, and that's the answer. Indeed, the important part of this is if I have two things in the same one of these disjoint sets, say X and Y both have the same captain, if they're both in the same set, they will both give me the same answer for the representative. All right? So I guess further to Hussein's question, the representative doesn't have to be any particular element as long as everyone in that set answers the same as to what's your representative. Yeah? So So in this kind of situation, I might have one set here with representative P. In this case, A of P, A of Q, and A of R should all be what is the representative of P, what is the representative of Q, what is the representative of R. All of these should equal P, because P was the kind of captain of that set. Now, it doesn't actually matter which one is designated the captain, as long as all three of these values are the same, right? But then you can use that and say, well, B of P, the number of things with representative P should be 3, whereas the number of things with representative Q and representative R, those should be 0. Right? And in much the same way, I would want the label of W, X, Y, and Z. All of these should have label X. X should know that it has 4 things in it, and the others should have 0 things in it. Okay? So again, it doesn't matter which one is the representative, as long as everyone knows who the representative is and they all give the same answer. Because now you can run things like find operations. You can ask find of, say, Y and W. Find of Y is X. Find of W is also X. So we know that they give the same answer, and therefore they're in the same connected component. Compare that to, say, find of R with find of Z. Find of R gives me the answer P. Find of Z gives me a different answer X, and therefore they are in different connected components. Right? Again, I haven't included the list array, whatever. The last operation to consider is what happens if I union these. What happens if I now get a new edge that should join, say, R and W? How do I do this? I would like to merge these two together into one big set containing 7 things. But I'll need to make some changes, right? First of all, I need to pick a captain for the new set. We can't have both P and X being representatives. We need to pick a new representative for all 7 things. And the way we're going to do that is we're going to ask which of you two has the most things under you. You're going to be the new representative. In this case, X would get chosen. We will then need to make some changes, right? All of these guys will have their representative changed from P to X. B of P should change from 3 to 0 because it's no longer going to be a representative of anything. And B of X should now gain those 3 things, right? So we need to change all 3 of these values to X, and we need to add this 3 to this 4 to make it up to 7 and replace that with 0. We also need to tweak the list array, but we'll mention that as we go. So how does this work? How do we union together 2 sets, I and j, with representatives little I and little j? I just want to mention first that when I'm adding this edge between R and W, as stated, we're not doing union of R and W because they're not representatives of anything, right? But instead what we can do is simply say, well, as soon as I place this edge, I should be unioning together P, which is the label of R, and X, which is the label of W. Alex, why not make B an array for arrays? Okay, there's too many words. There's too many, how to put it? The word array appears too many times in your comment. I can't understand you. I think what you're asking is, why can't B list everything with representative P rather than just the number of them? I think that's what you're asking. Well, that's what the list array does. So the B array basically just counts how many things are in the corresponding answer of the list array. Yeah. So what you're suggesting is just what the list array does. If you had an array rather than a linked list, then merging is slow. A linked list is really good because you can append one linked list to another in constant time, which is what we're going to want. Hussein, do we need to change the old representatives? Can't we look them up repeatedly? This is an interesting idea. The problem with your suggestion is exactly that. It's slow. Because we wanted the find operation. We wanted the find operation to run in constant time. Your suggestion is essentially making a tree, which means that you'd have to find parent, parent, parent. And so this now runs in not constant time, but kind of best case. Okay, there's some complications there, right? Depending on how you construct the tree, you might the height of that tree might be linear. If you construct the tree in a clever way, like we're about to do, you'll get the tree down to log n time, which is fine. But we've chosen an alternative way to do it. There is a way to improve that even further, but that's beyond the scope of the course. Okay, so he's saying there is some merit to that. You can do it in that way, but that's needs some needs us to do something a bit clever to both construct a nice, like a reasonably balanced tree, and the analysis of that is a little more complicated than what we're going to present. And finally, it's also just not the choice that we've made, right? If we want the find operation to run in constant time, we can't do that method. Okay, let's go on. So, how do we do union of I and j? Well, first, we're going to assume that I not... I guess so, yeah, you could put it like that. Yeah. Like there are only ever going to be n merges, like n union operations, whereas there could be m many find operations. So yeah, I guess that is true. Yeah. But in any case, we're looking to do find in constant time for this for right now. So that's going to be that's going to dominate. As in, that's going to rule out your suggestion, unfortunately. Okay. Suppose I have the two sets I and capital I and capital J, whose representatives are little I and little j. Without loss of generality, I'm going to assume that capital I is the larger of these two sets. Otherwise, we just perform the union operation the other way around. So we're going to interpret union ij as merge set j into set I. So we're going to make I the new representative of everyone in both sets, which means that for everyone in the small set j, I need to update their label from j, which it was before, to I, which it is now. I need to also update the number of things with representatives I and j. There is no longer anything with representative j, so that bj goes down to 0, and the old value gets added into bi. Finally, we need to glue the two lists together. So we previously had a linked list LJ, which had everything whose representative was j. That list needs to be appended to li. You can of course glue two linked lists together in constant time, and the new list LJ should be nothing because j is no longer the representative of anyone. Okay. Now, I think the part of this that should be concerning in terms of we're trying to do this efficiently is the second dot point. Certainly the third and fourth are constant time operations, right? But the second one seems slow because we need to actually do an update for everything in the small set. And, sure, the small set is smaller than the other one, but it still could have many things in it. So it should be concerning that we are doing a constant time operation for everything in the small set. And maybe this is slow. Maybe this is prohibitively slow. But as it turns out, it's actually fine. Let me show you why. The new value of bi is guaranteed to be at least twice the old value of bj. Why is this the case? Well, we knew that the old value of bi was bigger than or equal to the old value of bj because capital I was the bigger of the two sets. And so when we add together the old bi plus the old bj, that's at least twice the old bj, right? We're comparing 3 plus 4 against 3 plus 3, certainly the old bi and bj together is bigger than twice the old bj. And that combined value is the new bi. So the new bi is at least twice whatever the old b of j was. And why does this matter? Well, suppose we consider an element m of the smaller set. Its label am used to be j, and now as a result of this merge, it has changed to I. What's the impact of this? Well, its value. Sorry, let me try that again. Let's consider b of a of m. I'll mention later why that's important. But b of a of m used to be bj, right? Because a of m was j. So b of a of m used to refer to b of j. After the update, a of m is I, so it refers to the new b of I value, which means that b of a of m has at least doubled. Yeah, it used to be the old bj, it's now the new bi, and that is at least doubling. But what's the significance of b of a of m? What does this mean? Well, a of m is the captain of m. B is how many things have that same captain. So it's just the number of elements in this set containing m. All right? So the number of elements in the same set as m must have at least doubled whenever m's label changes. Does that make sense? Anytime that m's label changes, it must have been in the smaller set and getting merged into a bigger set, which means the number of things in its set went from size of the small set to size of the combined set, which is at least doubling. But how many times can you do that? How many times can you double? As a general rule, you can only double log many times, right? And that's going to be the key here. So remember we talked earlier about the total time taken by the first k union operations. I claim that those first k union operations can involve at most 2k many different elements of S. If you take k pairs of singleton sets, then that makes 2k many things. The only alternative is to reuse some elements, right? If you merge together two things and then you use that pair merged together with something else, you're not even touching any new elements. So the most number of distinct elements that could be affected by the first k union operations is 2 times k. Yeah. If you merge together x with y and then merge together z with w, that makes 4 things. But if you instead merge together x with y and then xy with z, you're only hitting 3 things. So, after the first k union operations, the set containing m is either a singleton set or it has at most 2k many things in it, right? Because only 2k of those elements were involved in the first k unions. But remember, how many times can A's label have changed? So M's label have changed. M's label was originally M itself, and then after doing some union operations, it may have changed, but every time that M's label changed, B of A of M at least doubled. That value was initially 1, it's now at most 2k, so it can have changed at most log base 2 of 2k many times. And therefore, repeating this for all the other 2k elements that have their label changed at all, we know that the first k union operations cause at most 2k times log base 2 of 2k many label changes in A. That is, changes in the label array A. Which means that the total, so if we flip back for a sec, in the first k union operations, those last 2 dot points each take constant time for each of the k things. So the total time spent in the last 2 dot points is theta of k. That's obvious. But we've now proven that the total time spent in the second dot point over all k of those operations is bounded by k log k, or rather 2k log 2k. So the total time taken by the first k union operations is indeed big O of k log k as required. So yeah, each union operation requires only constant time to update the size array and the list array. And the first k union operations take k log k time on the updates to the label array. So that's the dominant term. So the first k union operations take k log k time in total. And the version of union find that we've presented so far is sufficient to get the sharpest runtime on Kruskal's algorithm. But there is an improvement that uses path compression to how to put it. There's a bit of a trade-off here. You increase the complexity of find, but at the cost of reducing the complexity of the union operation. But hey, that's beyond what we need for this course. Again, you'll see more of the path compression optimization if you do Comp 4 and 2.8. Okay, so how do we actually use this for Kruskal's algorithm? If we have a graph with n vertices and m edges, we'll first sort all the edges. This takes time m log m because there are m edges to sort. But of course, m does not exceed n squared in a simple graph. So we can replace this m by n squared. So we have m log n squared. And using our log laws, we can kick the 2 down the front. And now it's a constant factor to be ignored. So this takes m log n time to sort all the edges of the graph. Next, we're going to run Kruskal's algorithm, that is, consider every edge in turn and either add it or not, depending on whether those two things are in the same connected component, i.e. whether they're in the same disjoint set according to the union find data structure. For every edge, we will find U and find V. If they're different, then we union the two things together. If they're the same, then there's already some path between U and V, so we toss it out. So every edge is considered using two find operations, and if it's to be selected, we also need to run a union operation. So in total, we may need to consider every single edge. So that requires 2m find operations, each in constant time, because you just look up an array of the A array, of an entry of the A array. We also have n-1 edges that are actually selected, so that requires n-1 many union operations, and the total cost of those is n log n, or n-1 log n-1, which is the same. And so the overall time complexity is m log n to sort, m for all the find operations, and n log n for all the union operations. Of course, the dominant term in this is the first one, m log n, because again, the number of edges is at least n-1. So we can simplify this time complexity down to m log n. Why is it 2m finds? Because for every edge you need to find u and find v. You need to do it for both endpoints to confirm whether they're in the same set or not. Yeah. Cool. Right. We are just getting to time, but before I wrap up, I'm going to present one more problem, which is an application of Kruskal's algorithm, and then we'll conclude. Again, if you need to go, I get it. You run along. Okay, so suppose we have a complete graph G where every edge is the distance between two vertices. So every single possible edge appears. By the way, I feel like I don't think I mentioned this in this section, but whenever we're talking about minimum spanning trees, we're always working with undirected graphs, right? Of course, initially when we defined trees, we were talking about undirected graphs, and the same applies here. So this is a complete undirected graph G where we have edge weights representing distances between every pair of vertices. Our task is to partition the vertices into k disjoint subsets to maximize the separation. That is, for every we want to partition them into disjoint sets so that if I consider every pair of points that belong to different sets, the smallest distance between them is maximized. And it turns out that all you have to do is do Kruskal's algorithm, but stop before you get to the end. So Kruskal's algorithm builds a forest where there are initially there are n many isolated vertices, and you start making small trees as you go, and eventually these all get combined into one tree. All that's required to solve this problem is you stop when you have k connected components rather than only one. So you add k minus 1 fewer edges. That's it. Now, why does this work? Suppose we run our Kruskal's algorithm. Suppose we consider running Kruskal's algorithm in full, which is you continue past having k connected components, and then say the next edge that you were about to add but didn't had distance delta. Then hopefully it's clear that delta is the minimum distance between two vertices of different connected components, right? And the reason for this is that every edge of length at most delta was either every edge of length at most delta has already either been included in my tree itself, in my forest, or it has been discarded. Either way, it joins two things that are already joined at this point, and therefore every edge of length at most delta is already accounted for. The only edges remaining that could join things in different components have length at least delta. But we're going to claim that this delta is optimal. And the way to prove this is by contradiction. Suppose there's a different partition into k subsets, which means that for this partition to be different from the one we found, we must have put two vertices VP and VR together, and the other partition must have put them separately. Yeah. So according to the other partition, these VP and VR are in different disjoint subsets, whereas our greedy, like following Kruskal's algorithm, put them together. Now let's have a look at the path here. Now, VP and VR belong to the same connected component within our Kruskal's algorithm, which means that there must be some, which means they're in the same subtree of the Kruskal forest, and therefore there's some path from VP to VR. Let's say that path looks like this. Well, that path must first leave, that path must go from within the alternate partitions set I outside of that set I to some other set. And let's say the first time it does that is from vertex Q to vertex Q plus 1. Well, we're now going to end up comparing this edge between VQ and VQ plus 1 to the original edge VP VR. We know that this edge VQ to VQ plus 1 is an edge that was chosen by Kruskal because it was on the path within the Kruskal forest, which means that its distance is at most delta. But this edge between VQ and VQ plus 1 is joining two different components of the alternative partition, which means the separation between clusters SI and SJ in the alternative partition is at most delta, and therefore the minimum separation in curly S is at most delta, which means that it's no better than what we found. And the proof is complete. The time complexity is reasonably simple to evaluate. The sorting takes n squared time. So the sorting of n squared edges takes n squared log n time. And running Kruskal's algorithm requires m log n steps. And again, the number of edges here is n squared. So this takes, again, n squared log n. So the total time complexity is n squared log n. All right. I'll mention here, by the way, that there may be an improvement on this using Prim's algorithm like using the array-based Prim's algorithm, precisely because this is the densest of all graphs, right? If you remember, when we talked about Dijkstra's algorithm, dense graphs were actually suited the array implementation. Sparse graphs did not, but this is a complete graph. It's as dense as possible. So yeah, have a go at analyzing the time complexity of. Oh, actually. Oh no, you can't use Prim, right? Sorry, what am I talking about? You can't use Prim's algorithm because Prim's algorithm doesn't add the edges to the forest in the same order, so it's not useful here. Please disregard that. I'm very sorry. Prim's algorithm doesn't help you in this problem. So this is indeed the best you can do. Okay. Before we wrap up, let's give you one more puzzle. I'm very happy that people have been discussing these puzzles at length on the forum. Let's keep that going. So this puzzle may be familiar to some of you from security and things like that. There's two people in different hotels. Bob wants to send a teddy bear to Alice using a lockbox. So there's this box has a padlock on it. Has an associated padlock which can be used to lock it. And now you have to send the teddy bear in with the constraint that A, when a non-empty box is sent, it must be locked. B, you can't send a key. The key has to remain with the sender. And C, you can't send an unlocked padlock. And so your task is to send the teddy bear from Bob to Alice while obeying all of those rules. And yeah, it's as some hints. A, you do need to make use of the fact that not only Bob but also Alice has a lockbox. And B, there are two different ways to do this, which either require 4 mailings or 2 mailings, the AND or the OR solution, respectively. All right, so I look forward to seeing some attempts at that on the forum, and that's all for today. All right, so good luck with the assignment. Again, that's due Thursday. We will have marks for assignment 1. We're aiming for Tuesday night. That's if everything goes very smoothly. They will be out before. They will be out before Thursday, so you will have at least a bit of time to look over the feedback from assignment 1 and incorporate that to assignment 2. Again, we're on a tight schedule. I'm aware that it's not a lot of time, but doing the best we can. Yeah. All right. Cheers, everyone. Also, just a reminder that Census Day is this weekend, so if you're considering dropping the course, the last day to do so without financial or academic penalty is this weekend. Again, you'll need to look up exactly what date and time it is. All right. All the best, everyone. See you in consult at 2:00 if you come along, or otherwise, see you next week. All right. Bye-bye.